All right. In the previous segment, we met up with the harmonic oscillator and worked through getting wave functions and energy expressions for it, right? At the end of that last video, we took a look at what the energy level diagram would look like with our energy levels superimposed on the parabolas that trace out the classical limits of the harmonic oscillator. Right. Summarize those features. We have quantized energy levels, so some energies are allowed, but most are not. The energy levels are equally spaced with the separation, the energy gap between energy levels. We could write that as h bar omega, which we could also write as h nu, right? So I could also call this h nu if I want, where nu would be, say, the frequency of light that would be absorbed to induce a transition between the two levels. The probability distribution for all the wave functions is symmetric about the center line of the potential well, right? Meaning the two sides are the same because that envelope that traces out the motion of the oscillator is a parabola, so it's symmetric, okay? And lastly, in the lowest energy state, the ground state, we do not have zero energy, right? We have 1/2 h bar omega, also 1/2 h nu. So we have a 0-point energy, just like we did when we looked at the particle in a box model. Right? I put in a slide here which quickly just compares or contrasts the energy levels for the two systems, the particle in a box on the left versus the harmonic oscillator on the right. In both cases, we have some non-zero energy for the ground state, right? So the lowest energy in both cases is above zero, right? There's a gap between my zero of energy and the lowest possible energy, right? We have a set of energy levels. If I labeled them with quantum numbers over here, this one says n equals 1, 2, 3, and so on. Over here, my quantum number, I'm going to call it V, I think, here, just to distinguish between them. This one can start at 0, and then 1, 2, 3, and so on, going up, right? The energy levels in the particle in a box model get farther apart as we go up the ladder, right? So if you picture those horizontal lines as being the steps or the rungs on a ladder, as you climb that particle in a box ladder, the steps get further apart. In the case of the harmonic oscillator, it's more like an actual or ordinary ladder where the space between adjacent rungs is always the same, right? In principle, with the walls of the box for the particle in a box being infinitely high and with my harmonic oscillator being a perfectly harmonic, a perfect spring, in principle, both of these things could go up to whatever level of energy we want, right? There's no limit, no maximum on the energy level. That is not going to be true for a real molecule because eventually if we put enough energy into a bond, instead of continuing to vibrate, it will break and then the two atoms just won't come back together, right? By the end of this video, we'll take a little bit of a look at how to move towards thinking about real molecules rather than purely harmonic oscillators. So, if I want to think about the probability densities, and we did look at the probability density functions for the quantum model at the end of the last video, think about a classical harmonic oscillator first, right? If you wanted to say what's the probability, what fraction of the time does my oscillator spend at various separations, right? So if my molecule is vibrating, my atoms are moving back and forth, as they do that, the distance, there's going to be some distances that are more likely than others. The reason for that is that the speed at which the masses are moving changes as they go across the range of values, right? When I'm right at the center where the equilibrium distance, where the spring is relaxed, then my system overall has only kinetic energy, right? The masses are moving, but there is no energy stored in the spring at that point. If I'm all the way stretched out, or all the way compressed, at both of those points, my masses have to stop because they have to change direction, right? So they have to go through a point where the mass is not moving. So at the limits of totally stretched or totally compressed, then my energy is all potential, right? And so what's going to be the most likely distance? It's going to be the distance that corresponds to having the masses not moving, because that's where they're going to spend the most time, right? That midpoint at the equilibrium separation, that's where the mass is moving the fastest, and that means it's going to spend the least time there, because it has to go through all the different points in each cycle, right? And so the fact that it's moving at different speeds means it will spend relatively more time at the stretched and compressed points and relatively less time at the center. So that's how the probability distribution would go for the classical harmonic oscillator, right? In the quantum harmonic oscillator, I should get something that my probability density just varies with psi squared, just like always, right? And so for the n equals 0 state, if we remember what psi looks like, for that lowest state, right? If the wave function, if these are the limits of my, my motion, my wave function squared looks kind of sort of like that, right? So in this case, its probability is greatest at the center and is smallest, goes to 0 over by the wings, right? So this is kind of the opposite of the classical oscillator, right? And that's a little bit of a peculiarity. If we look at how these would be for different states of the system, different wave functions, right? The n equals 0 case is up in the top left, right? And that's the one that I just sort of sketched out, where my quantum probability is peaked in the center. The classical probability is peaked fairly sharply towards the edges, right? Where in here, again, the center point, the point where I'm right there, that corresponds to having the spring be relaxed. It is neither stretched nor compressed. Right? And then the two sides of the parabola, one is the totally stretched out, one is the totally compressed. If I go up in quantum number, my classical probability basically always stays the same, right? It gets a little bit sharper, but it essentially just keeps sweeping out that it has the greatest probability at the extrema and the smallest probability in the center. As I go up through the quantum numbers, and it's a little bit strange how they go in this figure. I just found this someplace online. And so this is n equals 0, then this is 1. Over here is 2 and 3. And as that happens, you can see that the way the wave functions evolve, as n goes up, the wave functions, the maxima in the wave function tend to get a little taller over there near the edges. If I skip all the way up to n equals 10, then I've got a probability which is at least getting closer to looking like the classical one, right? Meaning the largest maximum is over by the edges, and the smallest of the maxima is in the middle, right? If I went in the limit of very high quantum numbers, where I got this thing extremely excited, very high energy, then my quantum probability would approach that classical probability shape, right? Because the general trend that we see here would continue. So these things actually come into agreement if we get to very high energies, okay? The reason there is that the total energy, the separation between the states, which is, remember, that's fixed, right? That's h nu or h bar omega. That energy separation is fixed. If I make the total energy larger, then the relevance of the separation becomes less, okay? And that's what makes it begin to tend in the direction of the classical prediction. So the reason why we're talking about harmonic oscillators is, as I mentioned in the introduction to this last time, is that we use the harmonic oscillator as a model for vibrational motion of molecules. We're interested in vibrational motion of molecules largely because we do vibrational spectroscopy for a variety of reasons. You're sort of familiar, if you think vibrational spectroscopy, think taking an IR spectrum, right? You are perhaps most familiar with doing that to identify a compound. If you've made something in organic lab, you might take an IR spectrum of it to confirm that it has the correct functional groups in it or something like that. Physical chemists often take vibrational spectra to sort out details about the structure of molecules. Some of our best measurements of bond lengths and bond strengths come from looking at vibrational spectroscopy, actually, okay? So the vibrations in molecules we generally treat as being harmonic. Why do we do that? Like many things, we do that mostly because it's the simplest way. Right. Again, towards the very end of this video, we'll look at what the more realistic situation is and say a few words about the validity of using the harmonic oscillator approximation. The simplest case to think about, and the one we will think about almost exclusively, is a diatomic molecule. That's the simplest because that exactly mimics the picture we've been using of two masses connected by a spring, right? In the equation for our harmonic oscillator, we have a frequency omega, which is the angular frequency, right? Square root of k over m. M is the mass, really the reduced mass. I probably should have put a mu there, but oh well. And k is the force constant. The force constant is a measure of the bond strength, right? And so if I measure those force constants, I can begin to rank different bonds in order of energy, various things like that, right? So there's a lot of things along that way we could do. We can also relate omega to nu, and we'll do that momentarily when we look at an example. Remember, nu is the frequency in, say, cycles per second. Omega is an angular frequency, so it is in just radians per second, strictly speaking. Although if you look at units on both those quantities, they both have 1 over second. So you have to be a little bit careful and make sure that you've identified the correct frequency to match what you're really looking at. So before we do a calculation, just a word about a unit, a strange unit known as wave numbers or inverse centimeters. All right. You may recall from looking at IR spectra, which you've probably done in say, an organic lab. But if you look at IR spectra, you may remember that the x-axis on the spectrum is often labeled in wave numbers or centimeters to the -1. Okay. Somewhat curiously, spectroscopists often use that unit as a unit of energy. Right. It's fairly obvious from looking at the dimensions that 1 over centimeters, that's got dimensions of 1 over length. That's not a unit of energy. Right. It's not a unit of frequency. Frequency and energy are proportional to one another, right? Because E is equal to h nu. Right. The wave number is also going to be proportional to those energies. So to get wave numbers, what it is it's 1 over lambda if you put the wavelength lambda in centimeters, right? Because nu, the frequency, is equal to c over lambda, that says that I can say that E is equal to hc over lambda, which means that it's also, I can get that directly by using my wave number, right? I could do hc times the wave number, and I would get that same effect. Right? And so wave number is proportional to both frequency and energy, and therefore it is often used in there. I remember when I first met up with wave numbers a long time ago when I was an undergraduate, it used to bother me considerably that we were using that for a unit of energy. I've kind of gotten over that over the years because it's just sort of standard practice. And so we will see those throughout the course when we look at spectra. So just try to get used to the idea of doing that. Make sure if you're calculating the wave number from a wavelength, you got to make sure you put the wavelength into centimeters if you're just doing 1 over lambda. Also, if you're converting between 1 over centimeters and 1 over meters or something like that, be really careful because it's very easy to do that in the wrong direction. That's kind of the word of warning I'll give about that. So we're going to do a little calculation for a vibrational frequency and a force constant, I guess, here, right? So the IR spectrum for carbon monoxide, the isotope numbers are on there just to set the masses because the frequency will actually change if we change the isotopes. We're going to calculate that a little bit at the end of the problem, I guess. This has its fundamental vibrational frequency, or its strong peak, exists at 2170 in wave numbers. Okay, and so the first thing we're going to do is find the force constant for this CO bond. Carbon monoxide has a triple bond in it, so the force constant we get should be a relatively large value as force constants go. Right, and we'll get some calibration of orders of magnitude from that. Then the second part I'm going to do is I'm going to find what would be the frequency, the wave number corresponding to the same vibration if I change the oxygen from oxygen 16 to oxygen 18. Right, that's going to shift the reduced mass of the molecule, and so we'll look at what would happen to the frequency or the wave number when we do that. All right, so let's see. We have our wave number there. Right, and the wave number often gets a symbol which is a nu with a tilde on it. Right, so if I want to get to actual frequency, nu is c over lambda, and one way to write that is to say that's c times nu tilde, where that nu with a tilde on it is the wave number. Okay, so what I'm going to do is I'm going to do that. In order to do this, c is the speed of light. In this case, to make life simple, I'm going to do the speed of light, and I'm just going to write 3 here, although in my notes it looks like I actually used several of the digits for some reason. I'm going to write this as 10 to the 10th centimeters per second. I'm going to do that because I'm anticipating that the next thing I'm going to do is going to be multiply that by the 2170 that's up above, which is in centimeters to the -1. Right? So when I do that, I multiply centimeters by inverse centimeters, and those disappear, so I'm left with 1/seconds. Right? And this says my frequency here is 6.5. I have digits written down, so I'll write them, I guess, times 10 to the 13th units of 1/second here. Okay. So that's my frequency. I guess I should have really set up a game plan for this in the first place. My K, what do I know about K? I know that omega, the angular frequency, is the square root of K over M. And for the M, I should write a mu. So let me actually do that and write a mu down there to make sure that I'm acknowledging that we need a reduced mass there. Okay, so that's how we're going to get to the force constant is from that equation. Right now I've got the ordinary frequency. I want the angular frequency, right? And so first I'm going to convert that. I'm going to say that omega, the frequency in radians, is equal to 2 pi times nu. Right? This is new because this is the frequency of the light that's being absorbed, right? And so if I do that, that's now equal to 2 pi times that number that I have up there. And that, according to my notes, is about 4.1 times 10 to the 14th. And I'm still in 1/seconds, although now that's radians per second instead of vibrational cycles per second. Now, I want to get K from omega. This is omega, and omega is up here. So if I take the equation up top and solve it for K, I will get K equals omega squared, and I need a mu. Right now, so far, I have not done my reduced mass. So let's do the reduced mass really fast. My reduced mass says mu is equal to the product of the masses, which I'm just going to do as whole numbers. These two are both very, very close to whole numbers anyway. And then on the bottom, I've got the sum. If I multiply that out, my notes say I get 6.86 in AMUs. And if you convert that to kilograms, we should get 1.14 times 10 to the -26th kilograms. Again, I think I mentioned last time, if you're stuck to convert AMUs into other mass units, you can always use the fact that a mole of AMUs equals a gram. And so to get from 6.86 to that 1.14 times 10 to the -26, I could divide by Avogadro's number and then divide by 1,000, and I should land at the actual mass, reduced mass in kilograms, okay? You can also just look up a conversion factor for that if you've got that handy. That's perfectly fine. Now we just solve for K, right? K is equal to omega squared. That was a really ugly omega. Mu, which is equal to my 4 times 10 to the 14th. And then now my mass is 1.14 times 10 to the -26. That's in kilograms. That gives me 1902. My units directly come out as kilograms per second squared, which happens to be the same as newtons per meter. Again, you can convince yourself of that if you expand the units in the Newton there, and you can cancel the meters and get to what we have showing there, okay? This is a quite large value for a force constant. Right? A lot of them are in hundreds in these units, right? So from a few hundred up to around there is sort of the range of values we would see. Remember, this is carbon monoxide, and it's got, if we just drew a Lewis structure, it's got a triple bond in there. So it's a strong bond, and so the spring that corresponds to that should be very stiff. It takes a lot of energy to vibrate my CO molecule, okay? All right, places, things that people sometimes mess up in there. One of them is just make sure you're being careful with whether you have omega or nu rather. The other is for the mass, make sure you're using the reduced mass. And then as in problems of all stripes, make sure you have the units making sense, because that's another one that people will do something a little bit off on and get things that are off by some orders of magnitude usually. There's a second part of the problem which says, what would the wave number be corresponding to the same vibration if we used oxygen 18 in the CO, right? So we make a heavier isotopomer of the molecule. And when we do that, we should move the vibrational frequency. To do this, we have to think a little bit about what's going to happen, right? What does that omega, that frequency depend on? Let's go from omega, right? Omega is the square root of K over mu. When I change the isotope, what's going to happen in that equation? I'm very definitely going to change mu, right? Because mu is related to mass. I'm changing the mass of the oxygen from 16 to 18. So that's definitely going to move my reduced mass a little bit heavier, presumably, right? If I look at the top is K, that's the force constant. When I add that extra mass to the oxygen, what am I doing? I'm putting neutrons in the nucleus of the oxygen atom, okay? That should not have any impact on the bonding in the molecule, because if I drew molecular orbitals for the two isotopes, they would look exactly the same. I have the same set of valence electrons, and so we expect the K to not change and the mu to change. This is why making substituting isotopes can be useful in spectra, because it would move a peak, and how much a peak would shift would depend a lot on how much that atom that we made heavier or lighter was actually moving around in that vibration. Right? And so we're going to say that the force constant stays the same, and only the mu shifts, the reduced mass shifts. So first I'm going to get my new reduced mass. My mu is now 12 times 18 over 12 plus 18. That comes out in AMUs to be 7.2. Which, if I convert that one to kilograms, I've got 1.2 times 10 to the minus 26th kilograms. If I just peek back at the notes for the previous one, we had 1.14, right? So we've shifted the reduced mass a little bit. In AMUs, it was 6.86 for the oxygen 16, and now it's up to 7.2. Right? It's not nearly as big a shift as when last time we calculated reduced masses and we changed normal hydrogen to deuterium, right? That was a doubling of the mass. So that was a big change, and that almost doubled the reduced mass. This one makes a much smaller shift. That's because now we've changed the mass, we've increased the mass by 1/8 rather than doubling it, right? So it has a much less pronounced effect on things, right? My force constant should still be the same, right? So I'm going to put down someplace over here, I'm going to say that we calculated K as being 1902. I'll say kilograms per second squared. We calculated that last time, and we're going to use that value again, right? So my new omega is equal to square root of K over mu, which is now square root of 1902. That's in kilograms per second squared. And on the bottom, I've got the new reduced mass, 1.2 times 10 to the minus 26. The kilograms will cancel. I've got 1 over second squared inside, so I'm getting 1 over seconds, which is good. And so that value comes to be 3. 98, about 4 times 10 to the 14th. Then I can say that nu is equal to omega over 2 pi. So I put that in there. And when I do that, I get 6.3 times 10 to the 13th. I want to get a wave number, and I've got actual frequency now, so I can say that the wave number, the nu with the tilde on it, that's just equal to nu, the actual frequency divided by c, the speed of light, and so that's equal to the number we just calculated. Speed of light, I'm going to put in again as 3 times 10 to the 10th, so that it's in centimeters per second. If I do that, I'm making sure that I end up on 1 over centimeters rather than 1 over meters. Right? I could get to 1 over meters, then I could convert as long as I'm careful with the units. If I divide that out, just to finish up, it looks like I get about 2114. Centimeters to the -1 as the wave number for the isotopically substituted molecule. So I went from 2170 to 2114. It definitely shifts the frequency. It doesn't shift it by an enormous amount. If we did a calculation like this for the HCl versus DCl case, the difference would be a lot more because the difference in the reduced masses was a lot more. Okay. One of the things to keep in mind from that calculation is the point that we made at the outset, which is when we change that isotope, we're changing the mass, so the reduced mass moves, but the force constant does not. Okay, if we had both things changing, then we wouldn't really be able to predict what was going to happen to the frequency, of course, because I would have changed both variables that were at work. All right. To finish up this one, what we're going to look at is a little bit about what a real molecule would look like, okay? This is a graph for a hydrogen molecule, which I definitely lifted from the website of a person named Brian Tissue, whose name is down there in the corner. Let's look at what we've got first, and it's got some labels on here that we're not terribly interested in just yet, but let's start off by checking out the axes, because I always like to do that first when we're looking at an unfamiliar graph. On the x-axis, I've got a distance, and it's in angstroms. Okay, that distance, that corresponds to, this is H2, right? So if this is a hydrogen, and this is the other hydrogen, right, they're bound together. This is what we're calling R, is just the separation, the center to center distance for that molecule, the bond length, okay? An angstrom is 10 to the minus 10 meters, if you haven't met up with angstroms in a while. On the y-axis, we've got energy, the potential energy in electron volts, okay? So what is that? That just says the energy, potential energy between the two atoms of the whole system is going to vary as that distance changes. Suppose we were out here at very long distances, where very long in this case corresponds to, say, 5 angstroms or more. At that point, my 2 hydrogen atoms are far enough apart that neither one knows the other is there, right? So there is no interaction between them. Right? This graph is a little bit unusual in that it has the 0 of energy at the bottom of the well. It actually would be a little bit more normal if the 0 of energy was up here, and then all the other energies would be negative, but that's not important to what we're trying to look at right now, right? If you come down here, the bottom of this thing, down here, my potential curve actually looks a little bit like the harmonic oscillator, right? Because the shape of that thing down near the bottom is fairly much like a parabola, okay? As I go up higher in energy, it gets progressively less like a parabola, right? Because what's happening is, as the spring stretches, it's overstretching, right? It's going further in one direction than it can in the other, right? They can go further apart than they can together. On this side, at short distances, the limiting factor there is I'm trying to take the 2 hydrogen atoms and almost literally put them on top of each other, right? So the nuclei are getting close together, and that produces a strong repulsion, which is why that side of the overall shape goes up almost vertically, okay? Over here, at some point, if I get up this high in energy, the molecule falls apart, right? That basically says it's like a spring. Any spring you have, if it's a real spring, if you stretch it far enough, you'll just unwind it, right? In this case, the bond, if we stretch it far enough, it'll break, and the one hydrogen atom will just not come back to the other, right? I get enough energy to overcome the strength of the bond, and that takes the molecule in half, right? Down here at the bottom, if I look at this distance versus that distance, where by distance I mean in energy, versus maybe that one, down here near the bottom of this potential well, the energy levels are reasonably evenly spaced, right? The gaps between there are pretty similar in size. Remember, the harmonic oscillator says they're supposed to be equal, right? So down at low energies, the vibration is acting pretty much like a harmonic oscillator, right? As I get higher in energy, you can see clearly if I go all the way up here, this spacing, these are much smaller than the ones in the bottom, right? So my energy levels in reality are getting closer and closer together as I go up the ladder, okay? That's due to what is referred to as anharmonicity, or the fact that the molecule is not really a harmonic oscillator, right? We could say it's an anharmonic oscillator, and the curve that's drawn there actually uses an equation that is a model for an anharmonic oscillator. It's got some free parameters in it that are just adjusted to fit data and things like that, right? So why is the harmonic oscillator model actually pretty good? It's pretty good because most of the time, most molecules, if we're anywhere near room temperature, the molecules are almost all down here in the bottom energy level. Okay, it turns out it takes enough energy to excite to that first vibrational level that for most molecules, if we're near room temperature, almost none of them get up to being in the V=1, the first excited state. Almost every molecule we look at near room temperature is sitting down near the ground state. So if we actually take an IR spectrum, we're looking pretty much exclusively at this bottom of the well, and down there it looks much like a harmonic oscillator. This general shape, the fact where this thing distorts here, right? This says that if I suppose I was in this energy level here, I didn't count to see what one that is, but it says that my molecule would stretch between the limits that correspond to the side. So roughly, oops, I went on the wrong one. Roughly between there and there, right? Meaning that, and the equilibrium distance, the sort of normal bond length is here. So that says it stretches out further on the long side than it comes in on the short side. Right? That's a normal feature of this anharmonicity, right? These quantities over here, since they're labeled, those correspond to dissociation energies measured or labeled in a couple of different ways. That would be a measure of the bond strength, or how much energy it took to break the bond in half, would be a literal interpretation of those quantities over there. We'll come back and look at figures like this one again in the next module when we talk about infrared spectra in some amount of detail. Before that, our next video will take up something called the rigid rotor, which is going to be our model for rotational motion for molecules. Thanks.